Assalamualaikum and good day. I be to Dr. Muhammad ARIF SAZALI and friends. Today, our group, which is from Group 1, are going to present on a report for Experiment 2 Single-Stage Compressor. Our group members are consist of 4 people. Me, Aliana Suha binti Muhammad Nasir, Nur Farisha Ikdina binti Muhammad Farid, Nur Izzatul Najula binti Muhammad Razif, and Putri Nur Emilia Roslina binti Muhammad Rosli. For introduction part, compressors are widely used for many engineering applications in day-to-day life. Compressors are classified based on design as reciprocating and rotary compressors. Reciprocating compressors are single-acting, double-acting, air-cooled, water-cooled, and single-stage. Multi-stage depends on the application of usage. Compressors are an open system that operate in a steady state. Around the world, compressors are most commonly used for a variety of applications. One type of compressor is the single-stage compressor, which is used in this experiment. A single-stage compressor is a machine that compresses and also pressurizes air to transform power into kinetic energy. To find the rate at which a single-stage compressor heats up, the temperature will be recorded once the power and motor are turned on and maintained there until the two readings are equal. Through the experiment, heat loss of the compressor will be identified. The objective of this experiment is to observe on how heat is converted to work in a single-stage compressor. Second is to determine the heat loss of the single-stage compressor. And third, to evaluate how quickly the compressor heats up. For the scopes part, to analyze the time taken for the temperature to be constant, or we call it as completely heats up in a single-stage compressor, and evaluate the heat loss of the compressor in steady state along the time interval.
So I will proceed with the theory of this experiment. In this experiment, pressure are inversely proportional to the volume. A single-stage compressor that we use in this experiment increases the pressure of gas by reducing its volume. This is achieved by using mechanical energy to compress the gas. A fixed volume of air is trapped between two sliding vanes powered by an offset rotor in a basic single-stage vane compressor as shown in figure 1. This amount of air is then subsequently pushed to the exit, reducing the area, thus the volume also decreases. As a result, its pressure rises and it's forced out of the outlet port. So these are the list of formulas that we use in this experiment. We calculated volumetric flow rate, mass flow rate, energy added to air by compressor, power out of motor, and heat emitted from compressor.
This is the experimental setup for this experiment. The first one, the cylinder tube, is air flow meter. Second is the current inlet valve. Third, inlet air pressure, P1. So the reading of P1 are taken from there. The fourth is air chamber. Fifth is electric power. The below is spring balance. Seventh is the motor. The eighth is rotary vane compressor. Ninth is the air chamber. Tenth is the outlet air pressure, P2. So you need to take the reading of P2 from outlet air pressure. And 11 is the rate inlet valve. And then the last is tachometer. We need to use the tachometer to measure the speed of the working engine. These are some close-up for the apparatus. As you can see at the first picture, this is the electric power apparatus. There are main switch, motor switch, power, speed, and also temperature. So the temperature T1 and T2 are taken from there. So since the speed reading for this apparatus is broken, we use the tachometer to measure the speed of the working motor. And at the below, this is the picture of the spring balance motor and also the rotary vane compressor. And then the last picture is the close-up of the airflow meter. You need to read the airflow meter from there, and then inlet air pressure and also outlet air pressure.
Next, I will go on with the methodology. For the step 1 is we need to fully open the green inlet valve. Next, we have to switch on the main power. And step 3 is we have to record the initial reading for T0, T1, T2 and P0. 4 needs to be done simultaneously, which is the first one is we have to switch on the motor. Then we need to start recording the T2 for every 1 minute intervals. After we have record the T2 for every 1 minute intervals, we have to fully open the red valve and we have to adjust the spring balance on the motor until the indicator is between two black lines. Step 5 is we need to record these 5 things, which are P1, P2, flow meter, motor spring balance and electric power. The next step is we have to use a tachometer to record motor speed, which is N. Step 7 is continue to record for T2 until we get the same rate. After finish doing all the 7 steps, we have to fully close the red valve and lastly switch off the motor and the main power.
These are the data that we got throughout the experiment. The initial readings of the parameters listed are taken at the beginning of the experiment. And here we focus on the outlet temperature, which is T2, against time. Below are the calculations involved during this experiment. The first one, we need to calculate the V0 using the formula V0 equals to RT0 over P0. So after we got the V0, we need to calculate the volumetric flow rate, which is V. V equals to V in over 60 times 10 to the power of 3. So we got the V equals to 0.005 meter cube per second. After that, we need to calculate the mass flow rate using the formula M equals to V over V0. So after we got the mass flow rate, we need to calculate the energy added to air by compressor, which is Hc. So using the formula Hc equals to MC in the bracket T2 minus T1, we got the Hc, and then we need to calculate power out of motor, and we also need to calculate heat emitted from compressor, which is Qc. There are 3 graphs that we got during this experiment. The first one is graph of outlet temperature T2 against time. As we can see, this graph has an increasing data, which means that as the time increasing, the outlet temperature increasing as well. Next, we have graph of energy added to air by compressor Hc against time t. As we can see, this graph is similar to graph 1, which has an increasing data, so it means that as time increasing, the energy added to air by compressor Hc is increasing as well. And the last one, we have graph of heat emitted from the compressor Qc against time t. It is shown that this graph is a bit different from the previous graphs, which it has a decreasing data, so it means that as the x-axis is increasing, the y-axis is decreasing. So in this case, as the time increasing, the heat emitted from the compressor Qc is decreasing. There are 3 things to be discussed in this experiment. The first one is, why is the heating up curve this shape? So there are 3 graphs were plotted in this experiment. First one is outlet temperature from graph 1, energy applied to the air by the compressor graph 2, and heat released by the compressor graph 3, and all of the graphs are against time t. Graph 1 and 2 represented increasing data, resulting graph 1 and 2 observe a heating up curve, while graph 3 represented decreasing data, resulting graph 3 observe a heating down curve. Heat transfer to a system known as heat gain increases the energy of molecules and the internal energy of the system, while heat transfer from a system known as heat loss decreases the energy as the energy transferred out. It is shown in graph 2 that value of energy applied to the air by compressor Hc has risen over time. It occurred because there is sufficient pressure and energy for the air to exit the compressor. The higher the energy applied to the air by the compressor, the longer it takes for the compressor to work. Second one is, what is happening to the energy that is being input to the system as it heats up? So, the air is heated by the compressor, which causes the temperature to rise and then level off before reaching thermal equilibrium. This demonstrates how energy enters the system, gets absorbed by it, and then escapes as heat into the atmosphere. The last one is, how does the amount of energy lost as heat compared to work input to compressor and when the heat is added to the air? So as compared to the work input to the compressor, the amount of energy lost as heat was smaller. The energy lost as heat, on the other hand, is smaller as compared to the heat applied to the air. The heat is generated by the compressor QC was the heat loss in this experiment, while the energy applied to the air by the compressor HC was the usable energy used to compress the air. The work input to the compressor was supplied by the motor's output power, which remained constant during the experiment. Energy cannot be created or destroyed, according to the first law of thermodynamics. Thus, in this experiment, energy input was transformed into heat emitted by the compressor and energy applied to the air. The statistics show that greater temperature differences result in greater energy applied to the environment and less energy loss. It indicates that the compressor performed more efficiently at a higher temperature.
For the conclusion part, based on the experiment, the outlet temperature T2 is increasing linearly, which is shown in the graph 1, from 48 degrees Celsius until it reached 125 degrees Celsius, where it remained constant after 29 minutes of heating. Next, the steady state occurs when the T-hour time, which is 29 minutes, as the heat emitted from the compressor QC remains the same at 199.08585 watt, and the energy added to the air by the compressor HC is 591.93615 watt. Then, as we know, during the heating process, the energy added to the air by the compressor HC is increased, while the heat emitted by the compressor QC will decrease. This shows that the energy can be converted as the input energy is turning into heat and sound energy. Hence, the energy added to the air by the compressor is increasing by when the time is increased in graph 2, while the heat emitted from the compressor is decreasing by the time is increasing, which is shown in graph 3. Besides that, the temperature will also decrease when the pressure decreases. For the safety procedure part, first, we have to make sure our eyes is perpendicular to the reading of manometer to avoid parallax error. Second, do not put finger too close with the motor while taking the reading of the motor speed, as it spins very fast to avoid any injury. Third, wear the heat-resistant glove while closing the red valve to avoid hands from burning. Lastly, this is our references that we refer in order to write this lab report.